Good morning, everyone. We are chemistry leaders from Johor Matriculation College. I'm Tan Chasin.
I'm Ong Wei Chen.
I'm Wong Yihan.
I'm Michelle Wee.
Today we are going to introduce chapter 2.4, which is Von-Haber cycle. Von-Haber cycle is a cycle that we're going to form a molecule in solid state. Von-Haber cycle is a series of chosen steps from elements to ionic compound for which all the enthalpies are known experimentally except lattice energy. There are 5 enthalpies involved and need to follow the order that I show. First, start with enthalpy of formation. We want to form solid. Then, enthalpy of atomization. From the solid, we want to change it to 1 mole of gaseous atom. Then, followed by ionization energy. Gaseous atom to gaseous ion. In other words, it is oxidation, release electron. Next, we have electron affinity. It happens at negative charge and it undergoes reduction. And last one is lattice energy from gaseous ion to solid. We have 2 methods to do it, which is energy cycle diagram and energy level diagram. There is 2 types of lattice energy, which is lattice formation and lattice dissociation. Lattice formation from gases to become solid. We use this in Von-Haber. The lattice formation release some of their energy so that they can form, so it will have a negative sign. And we use the lattice dissociation in the dissociation process, and it is from solid to gas. Ionization energy. Ionization energy is the minimum energy required to remove 1 mole of electron from 1 mole of gaseous atom. For example, once magnesium releases electron, it will have positive charge. Ionization energy usually have the positive value. Magnesium has 2 charges, so it will undergo first ionization energy and second ionization energy. Ionization depends on how many charges it carries. Besides, we have electron affinity. Electron affinity is energy change when 1 mole of gaseous atom gains 1 mole of electron to form an ion. It can be positive or negative since it is heat change. For example, chlorine gains electron and it looks like it undergoes reduction, while ionization energy looks like undergoes oxidation.
Okay, so now we are going into the exercises. First question, draw the Von-Haber cycle for the formation of MgCl2 from magnesium metal and chlorine gas. Calculate the enthalpy of formation of MgCl2. So, in the formation of MgCl2, we are finding the Mg and Cl2 from its most stable state. So it gives a clue here. The Mg metal, so it is in solid form. Chlorine gas, it is in gas form. So we are writing here MgS plus Cl2 gas to form MgCl2 and its enthalpy of formation are labeled here. Okay, so given enthalpy of atomization of Mg. So enthalpy of atomization means you need to change the solid to gas. So I'll label here positive 149 kilojoule. The first ionization of Mg, we are forming Mg plus in gas also. So I'll label here positive 740 kilojoule. And then second ionization of Mg, forming from Mg plus to Mg2 plus. So I'll label here positive 1456 kilojoule. The next one, enthalpy of atomization of Cl. So you can see Cl2 here in gas. So we need to form Cl atom. And you can see 2 Cl atom here. So we write here 2. And the enthalpy will also multiply by 2. And then electron affinity of Cl, we are forming Cl negative ion. And here too, so we have two atoms to form the ion. So the enthalpy of electron affinity we also need to multiply by 2. And now we have both ion in gas form. So these two we add up together, we can get the MgCl2. And then we have the lattice energy here. And then you can see actually this pathway is actually the same as this pathway. So the enthalpy of formation for MgCl2 is actually adding up all these to get it. So you can get enthalpy of formation of MgCl2 is positive 149 plus positive 740 plus 1456 plus 2 times 121 plus 2 times negative 369 plus negative 3933. So we'll get negative 2084 kilojoule per mole. And in the Born-Haber cycle, you don't need to put the per mole there, and you can just write the answer here. So here you don't need to put the per mole. Thank you.
So now we are going to construct a Born-Haber cycle and calculate the latest energy for the lithium bromide using the data given. So based on the data given, we are going to write down and list down all the equations first so that we can use it, and fully depends on the equation that we create when we draw the Born-Haber cycle. So for the first enthalpy of formation of lithium bromide, we will need to, based on the definition, which is we will form the lithium bromide in solid state, 1 mole of lithium bromide, from the most stable element, which is lithium solid and bromide gas. We need to make sure the equation is balanced, so we need to put 1/2 in front of the Br2 gas. So for the enthalpy of atomization of lithium, the lithium in solid state will turn into lithium in gaseous state. And for the enthalpy of atomization of bromine, 1/2 of the Br gas will turn into 1 mole of Br in gaseous state. And for the ionization energy of lithium, the lithium in gaseous state will undergo the ionization to release 1 electron and turn into the lithium plus ion in gaseous state. And for the last electron affinity of bromine, the bromine in gaseous state will turn into its ion, which is Br negative in gaseous state. So make sure you list down all the enthalpy at behind of the equation. So next we'll proceed to the Born-Haber cycle. First, you need to draw 2 axes and label your vertical axis as the enthalpy. We'll start from the first equation, which is the enthalpy of formation of lithium bromide. We first need to write down the reactant at any place, and you just label the starting point as 0. So refer back to your equation. The enthalpy of formation is negative 330 kilojoule. So since it's negative, so you need to make sure your arrow is pointed down. And you label your enthalpy and write down your product. So for the next equation, it's positive 107 kilojoule. So since it's positive, so you need to make sure your arrow is pointed outward. And you will do the same thing, which is you write down the product, which is your lithium solid now returns into lithium gas. And you just copy back the 1/2 Br in gases because we still haven't done anything on this element yet. So we proceed to the third equation. Your 1/Br2 in gaseous state now returns into the Br gas. So you copy back your lithium in gaseous state and plus with your product, which is Br in gaseous state, and you do the same thing. You label your enthalpy beside the arrow. So for the next, it's the ionization energy of lithium. Your lithium will release 1 electron and turns into its positive ion. So it's positive sign, so your arrow should be outward, and you label your enthalpy beside the arrow and write down your product, which is lithium plus in gaseous state, and copy back your Br in gaseous state too. So we proceed to next equation, which is electron affinity of bromine. You notice here the enthalpy now had become negative, so your arrow should be downward, and you label your enthalpy here and write down your product. Lithium plus, you still copy back from here, and now you write down the Br minus in gaseous state. So the next enthalpy is not given in the question, which is the things that we need to find now. So this is the latest energy, which the lithium ion and bromide ion now returns into 1 mole of lithium bromide in solid state. So the equations that we need to write down and find the latest energy is the enthalpy of H1, which is the arrow that pointing downward, equals to H2, H3, H4, H5, and H6. You can get these equations from, you determine the reaction in clockwise will always equals to the reaction which is anti-clockwise. So for now, your reaction in anti-clockwise, you only got one arrow, which is here in the blue one. So it will equals to the other reaction in the clockwise side. So you just substitute all the value into the equation that you get, and after you calculate, you can get our H6 now is negative 706 kilojoule per mole. Make sure you write the per mole in your final answer. And you can get the answer is in negative form, and the arrow down here, you can notice it's pointing downward, so this show that your answer is correct. And you need to write a conclusion to answer the question that lattice energy for lithium bromide is equals to negative 706 kilojoule per mole. And that's all for this question.
So now we need to discuss a partial question. And you can see the question is, based on the following thermochemical data, construct a bond-Haber cycle of sodium oxide and calculate the enthalpy of atomization of sodium. So first of all, we need to construct an energy cycle diagram, and we need to construct an equation which is solid state of sodium atom plus oxygen gas in gaseous state to form 1 mole of sodium oxide. So to form 1 mole of sodium oxide, we need to balance the equation by giving 2 mole of sodium atom and also half mole of oxygen molecule to balance the equation. And we can see in the questions, enthalpy of formation of sodium oxide is negative 414 kilojoule per mole. And next we need to write the enthalpy of atomization of sodium, which we are going to find in this question, which is convert solid state of sodium atom into gaseous state of sodium atom. So this is not given in the question, and this is an unknown we need to find. So we give the x for the question, and because this is 2 mole and 2 mole, we need to times 2, so this is 2x. Then we can see the question is given an ionization energy of sodium, and it means that to convert the sodium atom into sodium ion. So to convert into sodium ion, we also need to times 2 because this is 2 mole, and the ionization energy of sodium is 495 kilojoule per mole and times 2. And next we need to convert the oxygen molecule into oxygen atom. So we can see the question also given the first ionization. Note the enthalpy atomization of oxygen is 248 kilojoule per mole, because we need to convert the molecule into atom of oxygen, so we need the delta H of atomization of oxygen. Then the next one is we need to convert the oxygen atom into oxygen ion. So to convert into oxygen ion, we need the first electron affinity of oxygen, which is negative 141 kilojoule per mole. And we all know that oxygen is O2 minus, so we need to convert it twice. So we got here the second electron affinity of oxygen, which is 450 kilojoule per mole. So now we already get 2 of the ion, which is sodium ion and also oxygen ion. So we need to react these two to get the lattice energy of sodium oxide to form the solid state of sodium oxide. So we also got here the lattice energy of sodium oxide is negative 2479 kilojoule per mole. So after construct all the equation and also all the data is already converted into the diagram, we need to find the unknown, which we can know that the delta H of formation is the total energy needed for the whole cycle. So we need to add up all of this and also this one to get delta H of formation. So we need to construct an equation which is 2x, which is this one, plus with 495 times 2 kilojoule per mole, and plus with 248 kJ per mole plus negative 141 kJ per mole plus 750 kJ per mole and also negative 2479 kJ per mole and equals to this one, the total, which is delta H for formation, negative 414 kJ per mole. So after construct an equation, we can find that the X equals to positive 109 kJ per mole. So we can conclude that the energy of atomization of sodium is 109 kJ per mole.